Alright, so the first video topic we're going to cover today is the structure of the Earth and plate tectonics. And the reason we cover plate tectonics first is because it's a really big, grand, unifying theory of geology. A lot of stuff in geology that we study, different things like volcanoes and earthquakes and landforms, they're all tied together under plate tectonics. Plate tectonics influences all of those factors. You might have heard of a grand unifying theory of biology, like evolution by natural selection, right? Where nothing in biology makes sense except in light of evolution. It's the same here with geology. A lot of our geology and our Earth systems don't make sense except in light of plate tectonics theory, and so that's why we cover it first. So let's start with some geological background. We need to understand the structure of the Earth and the formation of the Earth to understand why plate tectonics works. So by our best estimates, lines of evidence show us that Earth is about 4.6 billion years old. And in the early formation of the solar system and the early formation of the Earth, we had a lot of stuff floating around, a lot of matter, a lot of rocks and minerals and things. And they're flying around in space and smashing together, falling together under gravity. And so this stuff ended up being really hot as the Earth formed. And it's hot for a couple of reasons. Number one is a lot of these minerals and elements were naturally radioactive. And if you're radioactive, you're throwing off a lot of energy, and that's generating a lot of heat. So we had a lot of hot stuff. But also this stuff is flying around space really fast. And if you're flying around really fast and then you smash into other stuff and you slow down very rapidly, what that does is it creates a lot of friction, and friction generates heat, right? So think about if we're in the college van and we're driving over Monarch Pass on Highway 50, and it's a really steep downgrade on the backside, and we're riding the brakes really hard. Those brake pads are pushing against the rotors and generating a lot of heat, and after too long the brakes will start to smoke and the rotors will start to warp and the van has trouble stopping, and we're in a really big problem. And that's all because of friction. So anyway, stuff is flying around the solar system really fast, smashing into each other, forming the planets, including Earth, and it's very hot. Okay, so if we have hot stuff and then it starts to cool, what happens when the minerals are all molten and very hot? Again, the Earth is pretty big, so it has a lot of gravity, and so gravity is going to pull the heavier stuff towards the middle of the Earth, and then the lighter stuff is going to go up to the top. So we can see here on the right-hand side of the slide, this is the layers of the Earth. The Earths were layered by composition. And so again, the heaviest stuff, so down here in the core, we've got iron and nickel, which are very heavy elements, right? So mostly iron and nickel. Here in the mantle, we've got somewhat lighter stuff. We have a lot of magnesium, Mg, and iron, Fe, right? So these are sometimes called silicate minerals or ferromagnesian silicates because they have iron and magnesium. And then in the crust, we have our lightest minerals, our lowest density rock. And the crust is just sort of a thin shell on the outside. And the crust has a lot of light minerals. So a lot of minerals, or a lot of elements like silicon, Si, and oxygen, and aluminum, and other things like that. And SiO2 is actually silicon dioxide, is the most abundant mineral in the Earth's crust, and that's quartz. It's the main mineral in a lot of rock and a lot of sand and other things like that. So again, heavy stuff in the middle, in the core, lighter stuff as you go out towards the crust. Now we can also layer those layers of the Earth by physical properties, so whether they're brittle and cool or solid. So the top part of the Earth, which includes the crust and part of the mantle, the upper part of the mantle, that's called the lithosphere. Litho meaning rock, and it's brittle rock. It's the coolest because it's on the outside, so it's cool, brittle rock that forms that kind of hard shell on the Earth. We can see here it's about 100 kilometers thick, but it varies. Ocean crust is much thinner, continental crust is much thicker, but this is made of our lightest minerals. Directly underneath the lithosphere, we have the asthenosphere. It's solid, but it's hot, very hot rock, and it's mobile. So you can think about if the crust or the lithosphere is the thin candy shell on the M&M, then the asthenosphere would be the chocolate, right? You can squeeze an M&M and you can kind of move it on that chocolate. It's solid, but it'll flow. It's mobile. And then as you go down here in the outer core, we have liquid again, so it's so hot down there that we've got molten rock. And then the inner core is under so much pressure that it's again solid. So again, layering by composition, we've got our heavier minerals in the core, lighter minerals in the crust. Layering by physical properties, we've got this hard shell, the lithosphere, on top of the solid but mobile asthenosphere. So the lithosphere is not one solid chunk, right? The lithosphere, our hard candy shell, is actually broken into several plates. And so here's a diagram of plates, tectonic plates. And those plates, where those plates come together, so the boundaries of the plates, are really where a lot of really exciting stuff happens in geology. So we can have plates pushing together. So the blue arrows on this diagram show places where plates are coming together. That's called a convergent plate boundary. Plates can slide past each other, so all the yellow arrows show the direction of plate movement where plates are sliding past. Or the plates can pull apart, and so the red arrows here are where plates are pulling apart from each other, and that's called a divergent plate boundary. So in places where the plates are moving past each other, either sliding past, coming together, or pulling apart, this is where we get really interesting stuff. Landforms, this is where mountains are formed, volcanoes, we have volcanic activity, earthquakes, all sorts of stuff like that. And so Colorado is right about here. I'm going to draw a little rectangle where Colorado is. And although you see we're not very close to a plate boundary, but in times in the past we were. And so just about all of the landforms, at least the big landforms of Colorado, have been influenced by plate tectonics at one time or another in the past. Here's just another diagram showing the major plates of the lithosphere. Again, brittle, hard plates sliding around on top of the asthenosphere. Now, the reason these plates move, the reason these plates shift past each other, bash into each other, and pull apart is because they're floating on the asthenosphere, which is that mobile rock, and there's heat moving through that rock. And the way heat moves from the Earth, moves through the Earth, is with convective flow. So down here, here's the core, right? And the core is still very hot. It's still got a lot of residual heat from the Earth's formation 4.6 billion years ago. And also there's a lot of naturally radioactive minerals down there. And so the radioactivity and the residual heat mean that that's really hot. The heat down here and the cooler area up here, we have a gradient, and that's called a geothermal gradient. Basically, it gets hotter the deeper you go, cooler towards the surface. Now, the heat moves through that rock in a convective flow. So you can see here, just like as if you put a pot of water on the stove, the heat's down at the bottom, the water at the bottom of the pot heats up, and it moves upwards, and then cooler water sinks to fill that place, and eventually you get a nice rolling boil, right? So the heat is moving the same way. It's moving up, and that pushes cooler rock out of the way, and then that cooler rock sinks, and the cooler rock gets heated, and it rises, and so on. And so we get this cycle going over and over again. So we can see here, this is a place where the plates are moving apart from each other, and that's a divergent plate boundary. And so the heat is, the convective flow is moving those plates apart, which allows some of this solid rock to melt because it's under less pressure, and so that stuff comes up out of that divergent plate boundary and creates new seafloor. Now over here off the west coast of South America, we see we have plates are coming together. So the convective heat is moving the plates this way and this way. And so here we have ocean crust, which is dense heavy rock, and it sinks. It's subducted underneath the continental rock over here. And so when that rock sinks, it drives water off into the mantle, which causes melting, and that molten rock comes up, forming these volcanic mountain chains here of the Andes. So here's another illustration of a divergent plate boundary. So this is a place where plates are pulling apart. And so we see the direction of motion is away from each other. And that allows this rock down here of the asthenosphere to melt. That rock is normally under a lot of pressure because of the overlying rock here. But as we stretch and thin that crust, it allows the rock to melt and then kind of ooze out. Molten rock is called magma. And when that magma reaches the surface, it's called lava, and it comes out here. Now this is dense, heavy rock from the mantle, right? Because it's deeper down, so we have heavier minerals, and so that comes up and it forms very dense, heavy rock of the ocean floor. Now here's a convergent plate boundary. So this is where plates are coming together. So here we have, this is convergent. And so here we have the Philippine plate and the Pacific plate out in the middle of the Pacific Ocean. So the Pacific plate, again, it's dense, heavy rock hitting the Philippine plate that's also dense, heavy rock. And so that one plate will subduct. It will sink under the other. And remember, this rock is saturated with water. That water gets driven off because of the heating as it goes down in depth, and that causes melting. So you can see the molten magma down here. That magma is less, it's molten, it's liquid, so it's less dense than solid rock, and it makes its way up through the crust, and eventually you can have volcanoes, and it can create things like volcanic island arcs. So here's a chain of islands, the Mariana Islands, related to a convergent boundary with both ocean and ocean crust on top. Here's another convergent boundary, but in this case we've got a piece of ocean crust and a piece of continental crust. So here again we're on the west coast of South America. And so we see here's the Nazca plate, and it's subducting underneath the continental South American plate. Now you see the continental plate is thicker, and it's also made of lighter rock. It's more buoyant. So you can't get continental crust to subduct. It's always going to float on top, and the oceanic crust is going to subduct underneath. And so what you see here, again, water driven off from the rock that's being subducted, and that melts the mantle rock underneath. That molten rock comes up through the crust and forms these volcanoes of the Andes Mountains. Now here's another convergent boundary, but here we've got continental crust. So we've got continental crust on both sides. So the Indian plate and the Eurasian plate. So this is where the Himalaya mountains are being pushed up over here on planet Earth. So continental crust, remember, it's made up of buoyant, lighter minerals, so you can't get it to subduct. So when a continental and continental plate collides with another continental plate, what you have is it just piles up really high mountains. So the highest mountains in the world here, the Himalaya range, are piled up because of that convergent plate boundary with no subduction. There's nowhere else for the rocks to go but up. And our last type of plate boundary is a transform fault boundary. So here we don't have any subduction, nothing's getting pushed down. We have plates moving past each other, sliding past. So for instance here in Southern California we have the San Andreas fault system. We have a lot of transform faults. The rocks slip past each other. So this rock is moving this way, and this plate is moving this way. So when they slip past each other, we have a lot of earthquakes, right? These massive pieces of rock are sliding past each other, releasing a lot of energy, causing vibrations to echo through the rocks, and that's where we have earthquakes. But we don't have any subduction, so nothing's really getting heated and molten, and with molten rock moving up. So we don't have any volcanic activity, just earthquakes. So, as I said, Colorado is not currently right on or very close to a plate boundary, but in the past, plate tectonic activity has thrust up mountains, has opened up rifts, and done all sorts of other things to generate these landforms, and these are the kinds of things we'll see on the field trip.